In this video, we're going to discuss the reactions of nitriles. Now, if you remember from the beginning of the chapter, we classified nitriles as acyl-like compounds. And this is mainly because they get hydrolyzed to carboxylic acids. And so the general reaction scheme is you take a nitrile, react it with water in acidic conditions, and you get a carboxylic acid. Of course, this can be done in both acid or basic conditions, just like we've seen with esters and we've seen with amides as well. So let's take a look at the mechanism of this reaction in acidic conditions. We see that when you have a nitrile in an acid, instead of, we don't have a carbonyl, but we do have this carbon-nitrogen triple bond. We know that the nitrogen has a partial positive charge. It's more electronegative than carbon is, and therefore, I'm sorry, partial negative charge. I think I said partial positive charge. A partial negative charge to it. And so it is the nucleophile, and it's going to undergo a proton transfer. And the result is that now I have the nitrile with the nitrogen protonated. And just like with carbonyls, when you protonate the oxygen, the carbon becomes the electrophile. So too with nitriles, the carbon more and more electron density is being withdrawn from the carbon, and so it can react with water. So the water attacks the carbonyl carbon, displacing a carbon-nitrogen triple bond, so pi bond. So if you think about the product that's generated from this reaction, we see that the carbon now has a double bond to nitrogen. The nitrogen has a hydrogen attached to it, and now I've added water to that carbon. Of course, water still has two hydrogens on there, so it has a positive charge. And if we simply then deprotonate the hydrogen from that water that added, we're going to then generate a neutral product. And that neutral product now looks like this. So RC double bond NH with now an OH. And of course we regenerate our hydronium ion as the acid. So if we think about the next step, we're going to get proton transfer. The nitrogen pair of electrons can get protonated, and we generate our C double bond NH2. So now the nitrogen has a positive charge. And of course, you know, we can think about this in one of two ways. This actually has a resonance structure to it, and that resonance structure, you can draw a pair of electrons from the oxygen down to form a carbonyl, C double bond O, and displacing the carbon-nitrogen pi bond. And so we get something that looks like this. Now we can start to see the carbonyl forming, right? And which we certainly have a carbonyl, and all it is a protonated carbonyl. And I can take water and I can deprotonate that carbonyl, just like so, and I generate an amide, right? So nitriles get hydrolyzed to amides. And of course, notice I'm also regenerating my acid, my hydronium ion catalyst. The water gets protonated to generate the hydronium ion. And what do we know about amides in aqueous acidic conditions? That's right? They get hydrolyzed. And so that hydrolysis is then going to produce our carboxylic acid. So nitriles go to amides, the amides go to carboxylic acids in that hydrolysis. So nitriles can also be hydrolyzed in basic conditions as well. And we're going to take a look at that mechanism, just kind of see the various subtleties, the slight differences in that particular mechanism. All right, so basic hydrolysis. We saw basic hydrolysis of amides, basic hydrolysis of esters, right, saponification, and now we see basic hydrolysis of nitriles. the nitrile in basic conditions, hydroxide in water, that's what we're using. So the hydroxide acts as a nucleophile right away, attacks that carbon of the nitrile, displacing a carbon-nitrogen triple bond, pi bond. And so we generate an anion where the nitrogen has a negative charge associated with it. And that anion is a very strong base. So we can use water to transfer a proton to that anion. And now we have a neutral species. And of course, we've regenerated hydroxide ion in the process. So that hydroxide ion can then simply remove a proton from the OH. And notice I generate a species where the oxygen has a negative charge, but I can think about a resonance structure of that this intermediate in which I donate a pair of electrons from the oxygen down to form a carbon-oxygen pi bond, and then the electrons from the carbon-nitrogen pi bond will go to the nitrogen. And the result of this is, notice I'm forming the carbonyl, and now the NH, the nitrogen, has a negative charge, and if I simply protonate that with water, I generate an amide, right? Just like in acid hydrolysis, I get to the amide. In basic hydrolysis, I also get to the amide. And of course, we also know that we're regenerating hydroxide in the process. So hydroxide in water and an amide, we're going to undergo basic hydrolysis. In basic hydrolysis of amides, you end up getting a carboxylate plus the ammonia, and so we have to acidify it to generate our carboxylic acid plus the ammonium salt. So, think about patterns. Again, patterns, patterns, patterns. If you can get the patterns down, the mechanisms are actually relatively straightforward. Now, nitriles will also react with organometallics. And again, it's an addition reaction. Again, the mechanism is somewhat similar, although there's a little twist, and we can kind of understand the product formation if we observe the mechanism of this reaction. We can kind of predict what's going on. So here I have a nitrile and I have an organolithium or a Grignard reagent. Doesn't matter, either one reacts. So what's going to happen? Well, we saw with hydroxide adds as a nucleophile, good nucleophile, adds to the carbon. Organolithiums, also very good nucleophiles, and so they can add to the carbon, displacing that carbon-nitrogen pi triple bond. So the result is, again, this negative imine salt, right? It's called an imine salt, and that imine salt can that's the result of the reaction of an organolithium. So very similar to the reaction of ketones and aldehydes, organolithiums will react with these carbon pi bond systems, and you generate a salt. And so then what do? We, in a subsequent workup, we add water and an acid to it. And in that process, what happens is the imine salt gets protonated, and you generate an imine. Now, keep in mind what conditions we're in. We're in water, and we have an acid present. Imines, as we learned back in the chapter of aldehydes and ketones, reactions of aldehydes and ketones, imines are in equilibrium with their ketones. And if you place an imine, just like you place an acetal in water under acidic conditions, it reverts back to the ketone. So our imine here is now going to undergo hydrolysis in these aqueous acidic conditions and produce our ketone, right? So nitriles produce ketones when they react with organometallics. And this is how, a fundamental understanding of the mechanism kind of shows us how that process happens. So let's look at an example here. I have phenyl nitrile, and I react it with methyl magnesium bromide in ether, followed by an aqueous acidic workup. So the methyl is going to add to that the carbon, forming my imine, and then that imine is going to be hydrolyzed to the ketone, and therefore I get a methyl phenyl ketone, or acetophenone in this case, right? So this is called acetophenone. And nitriles will also react with metal hydrides, and metal hydrides reduce nitriles to primary amines. Just like amides get reduced to primary amines, nitriles also get reduced to primary amines. So if I have some generic nitrile, I react it with lithium aluminum hydride in some aprotic solvent, ether, THF, followed by an aqueous workup, I get RCH2 NH2. So notice I have 4 hydrogens adding across that triple bond. So the triple bond gets completely reduced to a single bond, 1 sigma bond. All the pi bonds are gone now, and I have a CH2 NH2 in its place. The tricky part here is keeping track of all the carbons, right? Cyanide, the nitrile, has a carbon attached, and that carbon is getting converted to a CH2, and the nitrogen is getting converted to an NH2 as well. So when I look at a particular structure and I have lithium aluminum hydride as my reagent, I know that I have to write the carbon. Notice that CN is CH2 NH2. So one common mistake students make is forgetting that carbon there, and they'll just put an NH2 group on there. That's not the case, right? So the carbon gets reduced, the nitrogen gets reduced as well. And of course, we can also reduce nitriles using catalytic hydrogenation. So if I take, here I have phenyl nitrile and react it with hydrogen over palladium. We know that hydrogen will reduce pi bonds. It doesn't reduce benzene very easily, but it can reduce alkenes, and it can reduce alkynes, and it can reduce carbonyl groups, and so it can also reduce carbon-nitrogen pi bonds as well. And the result is the same as that of the reduction using a metal hydride. So nitriles can be reduced with metal hydrides, or they could be reduced with catalytic hydrogenation, and the result is the same. You get primary amine.